got 5% wrong.
Yeah.
This is not your everyday stupid. This is advanced stupid.
Okay, let's look at this last question about vector fields. So these first three are what? These are like R2 vector fields, right? So they would be from R2 to an R2 vector. So in other words, and those are the ones we talked about last time. So like so what's the independent thing in here? What's the independent thing? So what goes into this function? A location, right? A location, an ordered pair x and y. And then what comes out? What's the dependent thing? What is that? So given a location, the function f gives back a vector. Okay, so given a location in R2, we get a 2 vector, or a 2-dimensional vector. And that's what all these first three are. So let's look at number 3. So if we were to write this, we could write it this way. So it just says I. So what's the what's the x component and what's the y component of all these vectors? What's the x component of these vectors? So we're not going to use the basis. We're not going to use basis anymore. We just want to know what function of x and y is the x coordinate or x component of the vector. It's not x. 1. It's 1 times I, right? And then what about be 0? So what we're talking about is no matter what the location is, no matter what location you're at, the vector you have is always 1, 0. That's what that's saying. Or 1i plus 0j, right? 1i plus 0j. So that should be a pretty easy vector field, no matter where you are. So what is the vector 1, 0? No matter where you are, you get the vector 1, 0. Can you imagine that? So if I'm here, it's just a 1-unit vector. Which direction? To the right. If I'm here, same vector. So it's like, what is it? Like it's like a river flowing east at a constant speed everywhere of what, 1 foot per second or something like that. No matter where you are in the river, the current is 1 foot per second directly east. That's an example of that vector field. Okay, what about this one? So if we were to write number 2. So how can we write it in component form rather than ij form? So we've got, what do we got here? What's the x component of these vectors? Negative y. And what's the y component? X. Is that our example? That might have been our example last time, something like that. Okay? So if I'm at the point, say, 2, 1 in this vector field, what vector do I have at the point 2, 1? You want negative 1, 2. Agree with that? So in other words, f of 2, 1, so location, independent, or input, gives us the vector. 2 people are saying negative 1, 2. Agree with that? That's right. So based on this vector field, at the point 2, 1, the vector there is negative 1, 2. So here's 2, 1. So now I'm drawing a new one here, new vector field. I'm at the point, what did I say, 2, 1. Then I have the vector negative 1, 2. Negative 1, 2, like this. And if I'm at the point negative 1, 1, or say negative 1, negative 3, positive 2. If I'm at negative 3, positive 2, negative 2, negative 3? Yeah, so if I'm at the point negative 3, positive 2, then it's going to be negative 2. The vector will be negative 2, negative 3. So what's going to be the overall effect of this one? The further out away from the origin I am, the larger the magnitude of my vectors, right? Because I've got bigger coordinates means larger vectors because they're just based on x and y. So as I get further out, I'm going to have larger vectors. And then we could kind of do one in each, but I think this is going to be kind of like a big whirlpool, like this. So if I'm in the third quadrant, they're going to point down and to the right. If I'm in the fourth quadrant, all the vectors are going to point somewhat up and to the, down and to the right, and then up and to the right. Okay, so imagine a whirlpool. Then the velocity of the water increases as you get further away from the origin. Okay, what about this first one? X, Y. X, Y. What's that vector field like? What's that? Expanding out from the origin. Because if I'm at the point, say 1, 4, what vector do I have? 1, 4. If I'm at the point 5, 0, what vector do I have? 5, 0. So if you imagine the vector from the origin to my location, then is the vector at that location, right? So if you think about, say, negative 2, positive 3. Well, here's the position vector that gives me the position, negative 2, positive 3. Well, then that is the vector at that location, negative 2 and positive 3. So again, vectors close to the origin will be the smallest. As you get further away from the origin, they will get larger. And every vector will point directly away from the origin. The component's the same as the location. So this is like expanding out. We're expanding out and increasing speed as you get further away. Always expanding in direction directly away from the origin. Okay, so keeping that in mind, so we want to look for, so then there's 6 choices. Now the other choices are, there are 3 vector fields, meaning you get for a point in space, you have a 3 vector. All right, so like this one we can just look at and kind of figure out what it is. What's this? It's the vector field x, y, z. So every vector is the same as its location, right, in space. Every vector is the same as its location in space. So it's the same thing. It's the 3D version of what we just talked about, right? Yes. It's the 3D version, just everything expanding away. So we should be able to find these 4. And so if we draw these in R3, then we're just going to get the same vector field at every z value, right? For these, doesn't matter what z is. So if you slice it at any z value, you're going to get the same vector field that we're just talking about in R2, right? So we'll be on the lookout for that. And then this one should be easy to spot because as you get further away from the origin, the vectors just get greater in magnitude and always pointing directly away from the origin, right? So let's see if we can find those 4. So we got number 2 is the whirlpool, number 1 is expanding in R2, and number 3 is just that 1, 0, and then x, y, z. So here we go. So how about this one? So if I look down, so is that, what was it, negative y x?
Yeah.
So do you see that it's the same no matter what z is? It's the same vector field for all z, and it's exactly what we said, right? It's that counterclockwise whirlpool. As you get further away, those vectors get larger. So I think that's number 2. Is that number 2?
Yeah.
Okay, what's this one? Let's see here.
Number 3.
So I want to get the x. Z is here. There we go. Let's see if we can orient x and y this way. Come on. Oh, it's hard. I'm trying to, maybe, won't let me do it. Maybe, almost. Trying to turn it. Okay, I think that's the best I'm going to do. So which one's this? 1, 0, right? So it's the same for every z value. See those z values up and down now? It's the same for every z value, and it's just every vector is 1, 0. Every vector is 1, 0. Turn that a little bit further. I have trouble doing that. Okay. How about this one? I think that's one that we didn't work on. As you get further away from the origin, these vectors are getting smaller, right? So it's something else. It's one of those 2 that we didn't talk about. All right, how about this one? So is it 3-dimensional, or is it R2 or R3? R3. This is x, y, z, right? X, y, z. Everything's pointing directly away from the origin, and those vectors are getting greater as you get further away from the origin. This is just x, y, z. The location, the vector is the location, right? The vector is the same as the location. And that's just expanding in all directions, right?
Yep.
What's this? Another one we didn't do, right? Expanding in all directions, but smaller as you go away. So that's another one we didn't do. So what's this last one? Is this R3 or R2? It's shown in R3, but it's really just there's no z. It's the same for every z. So this is what? XY, right? XY. So if you're looking straight down the XY plane, vectors are, this is expansion in R2, basically. Expansion in R2, away from the origin, vectors get larger, and your vector at any given spot is the same components as the location. Okay, any questions on this? Trying to get a feel for vector fields, just trying to get oriented to these things. All right. So let's try this. So all components are either, so the components are either plus or minus x, plus or minus y, plus or minus z, plus or minus 1 or 0. So, for instance, it could be, it's just an example, negative z, 1x. I just pulled that out of the air. Okay. So the x component could be any one of these 9 things. The y component could be any one of these 9 things, and the z component could be any one of these nine things. Plus or minus x, or plus or minus y, plus or minus z, plus or minus 1 or 0. Okay? So I'm going to slowly move this thing around, and it's going to be up to you to decide what this is. So this is looking straight down in the xy plane, but positive x is this way, positive y is this way, just like our R3 orientation. Here's looking at the yz plane. Here's looking at the xz plane. We got some stuff going on there. All right, so why don't you I'll leave it here. This is looking at the yz plane. So why don't you decide could you figure out anything from just looking at the yz plane, any of the components? Talk. Okay, you want to maybe change it or leave it? So this actually kind of gives you like 2 of the components by looking at this view. Okay, so now if we look down, I'll orient it so here's x looking down on xy. There we go. This is looking down on xy. No, this is I've got this y and x, like the way you're used to seeing it. This x and y. X is to the right, y is up right now. All right, ready for another one? Here we go. Here's looking at the YZ plane. This is number 2. This is number 2. We can go back to the first one if you want to talk about that more. Here's number 2. This is the YZ plane. So this is our normal view of the R3 system. So you're looking right at the YZ plane right now. Positive y to the right, positive z up. Here's XY plane. Are we good, or do you want another view?
I think we're good.
So just to check, here's a check. So this is what? This is XZ. X to the right, Z up. There's your XZ view. You guys got it?
Yep.
Well, they got it in the front. How about in the back? Thumbs up. 2 thumbs up. All right, let's do one more. These fun? All right, maybe this is more of a challenge. I hope. Let's do y, z.
Whoa.
So the brightest color is closest to you. And then as you go back, so back negative x, they kind of get gray. Okay? So can you see that? So the brightest colors are the ones closest to you, and then as you move back in the negative x direction, more gray. All right, we'll come back to this one. Let me show you the xz plane. Let's do this one. How about this? Here's the xz. X to the right, z up. X to the right, z up. Another view?
Yes. I'm trying to figure out why.
Here's the xy plane. Again, so the brightest pink ones will be the greatest z, closest to you. And then as you go back, as z decreases, they become more gray. Go. So other people got? Yeah. Gray. So it's the most colorful will be the ones closest to you. The largest z values. Yeah, positive z. And then as you go, yeah. So two of these will be for positive z. Like this will be the greatest positive z, and then a smaller positive z. Then it'll be a small negative z, and the largest negative z. Yeah. So these are going. These last two would be for negative z. Back. What do you guys think? Jonathan, did you get it? Wait, what did you think? This last one, yeah. Okay. Leo, what did you get? Brandon? Any other chord? Did you get any other components? So one of those components you can see pretty clearly in this view. Yeah, I mean, look at the y. What about the y component of these vectors? Yeah, they're all up the same amount, right? So the y component is 1. Mark and what did you guys get? Z1x. That seems like to be the consensus. Good job. So what does that mean? It means that the x component of these vectors is the z coordinate of their position. The x component of these vectors is the z coordinate of their position. Trying to get a view here. There we go. So what does that mean? As you move, so this is YZ plane again. The x component, the amount that the vector changes in x is how high up or down you are. Is that right?
It's where X is. Depends on how high.
So how much x changes, the change in x, the x component of each of these vectors is that, I'm not seeing that. How's that working? X component. Oh, right. I'm thinking to the right is x. Okay. So let's do it. Let's look at this. Let's look at the XZ plane. I think that's the one that gives it to you. So how much each of these vectors changes in the x direction is the same as how high up or down you are. right? So if you're up here, these have the greatest change in x, and then a smaller change in x, and then a negative change in x, and then a greater negative change in x. So the horizontal change is your vertical position. That's what this says. And then similarly, your vertical change, how much it changes up and down, horizontal position. So this is the greatest vertical change because it's the greatest x. And now x is decreasing, so you have less of a vertical change. And now x is a little bit negative, so you have a little negative change in z. And now x is more negative, so you have a bigger negative change in z. And that's the same no matter what z you're at. Okay, any questions on this? Okay, so I want you, I'm going to change some things up on the screen, and while I'm doing that, I want you to we talked about something called a gradient in this class. So I want you to talk to the person next to you. What's everything you remember about the gradient? Recall as much as you can. Don't look at your notes, just talk it out. What's everything as much as you can remember about what we call the gradient? Go. Okay, so first and foremost, what is a gradient in a word? In one word, what is a gradient? Yeah. Okay, so a vector. It's a vector. That's what I said. In a word. I said one word to start. But yes, just give me a second. So a gradient vector is, okay, now keep going. So a gradient vector is? Okay, good. So a gradient vector is, so what was our notation for that?
Function x, y, x, or fx basically is what we do.
Right, so it was this.
Yeah, we did fx.
Let's make that clear. All right, so that's how you calculate it, right?
That's just the 2.
So gradient vector was what? It was the partial derivatives, right? It was the partial derivative of x and the partial derivative of y made into a vector, right? Made into a vector. Okay? Somebody new, tell me something else about a gradient. Yeah?
It's essentially the slope of the surface at that location.
Okay, so, but remember, at a given location, we had lots of rates of change.
It's the greatest.
So, yeah, Chris?
The direction of that gradient will be the maximum rate of change on the surface.
Okay, right. So it's that vector then is a two-dimensional vector indicating the direction of the greatest derivative, right, or the largest rate of change. Okay, good. And so yeah, and you can kind of think of the slope of the surface as the greatest slope of the surface. Any other slope is like a kind of a component of that. So it's not wrong to say that it's the slope of the surface at that point, just as long as you know that it's the greatest slope or the greatest rate of change. Okay, somebody new, what else? There's more to it. The gradient vector is, and it indicates the direction of greatest rate of change. And there was at least one more thing about it. Somebody's thinking it. Don't be shy. It tells us something else. Besides the direction of greatest rate of change, it also tells us
Direction of least change?
Yeah.
The magnitude.
And what is the magnitude of the greatest rate of change?
It's the square root of
Right. And what are you finding when you find that? Yeah, exactly.
That's the magnitude.
Yeah, so the magnitude of that vector is the magnitude of the greatest rate of change, right? So the direction gives you the direction of greatest rate, and the magnitude of it is the magnitude of the greatest rate of change. Okay, so and why are we specifying greatest rate of change? Why? Because what the direction that you go, that the rate of change changes, right? If you're standing on the side of a mountain, the direction that you start walking in will determine what your rate of change. Will you take a step down? Will you take a step up? Will you walk horizontally, right? So the gradient vector is like if you're on the side of a hill, the gradient vector is going to point in the direction of steepest ascent, greatest rate of change on that surface, and then the magnitude of that gradient will be the rate of change that you encounter if you go that way. Okay, so then what would a gradient field be? A gradient field would be, so you have a surface, you have a function, and you're going to have the gradient vector at every location, right? So at every single location, x and y, there is a gradient vector. So if you put all those, so this is exactly what a vector field is, right? Given a location, you get a vector. So what if, given a surface, for every location, you map out, or you have a function that tells you what the gradient vector is at every location? That's what we call a gradient field. So gradient field So it's really the same thing. It's still this. It's just before we were always talking about it at a specific location. We said, okay, here we're at 4, -3, the point 4, -3. What's the gradient vector? Well, now we're just going to make a function out of that. Given any location, any ordered pair x and y, what is the gradient vector that you get? That's what a gradient field is, a vector field. So the only difference now is, we would say, at any given point x, y. So we just take what we had before as a gradient vector, and we make a function out of it. Right? Now just say, let it be any, let your independent be any location, and then the dependent value, like in vector field, would be the vector at that point, and now and specifically the gradient vector. So the surface, is that sketched in R2 or R3? I heard both. Does that surface get sketched in R2 or R3? R3, right? So this is z equals x squared plus y squared minus 3, right? So it's going to be R3. The gradient field, is that in R2 or R3? That's a 2 vector, right? That's going to be the partial with respect to x and the partial with respect to y as functions of x and y. That's R2. Okay, and the last thing is explain how the gradient field is consistent with the surface that you drew, right? So why are they a match, right? Why is the gradient field that you drew a match to the surface that you drew? What's that?
The second one?
Okay. What is the surface?
Yeah, probably.
Okay, hopefully you decided that was a paraboloid, and its vertex is at?
-3. 0, 0.
0, 0, -3, and it opens, how does it open?
For the Z.
On the positive, it opens on the positive z-axis, right? And is it elliptical or circular?
Circular.
Circular, right? This is like the most basic circular kind, right? So it's x squared plus y squared. Okay, and so let's see that. Is that what you sketched? Is yours turning?
No. I made it through my spin. I have a slice.
-2. It's not turning. Just kidding. All right, so then what about the gradient field? So what did you get for the gradient field? XY plane, but that's fine, right? So now, why does it make sense? How is the gradient field consistent with the surface? What is it showing about the surface? So the gradient field,
It's still circular. Showing the circular form, basically.
okay, but what does each gradient vector show? Yeah.
If you look in if you look straight above, it, whatever is in a circular pattern, that's like one contour of the, it's like one layer of where Z is, and then it's just the further you get out, it's just a higher Z value.
Okay. All right. So given a point on this surface, what could you say about the gradient? Given any point on the surface.
It's increasing as it gets further from the origin.
Right. So at any given point on this surface, the direction of steepest ascent will be directly away from the origin, right? Directly away. You'd walk directly away from the origin to go in the direction of steepest ascent. And then these magnitudes of these vectors tell us what that rate of change is. And those rates of change are going to get greater as you get further from the origin, because what does the paraboloid do? It gets steeper as you move out, right? So as you get further away from the z-axis, it gets steeper and steeper, and so that's why these vectors get larger and larger further out away. This one. Okay? So for your sheet, z equals -x plus 2y plus 3. So let's, let's find the gradient field for the surface and sketch the gradient field, and then explain why the gradient field is consistent with the surface. Are we good? You guys are pretty quiet. Are we good? All right, so how would a gradient field then relate to a contour plot? So remember where the contour plot was? Contour lines were lines that showed what? Each line shows what about the surface? What's that? A constant z value, right? That's a certain z value. So if you have a contour plot, each line is a constant z value. And remember how the gradient vectors related to that. So I want everyone to think about it. So so those are both xy constructs, right? The contour plot and the gradient field are both, we could put those both in the xy plane together. And what would you see? What would the relationship be? Talk to the person next to you. All right, now I'm showing a consistent, here, the part of the gradient field I'm showing, or the part over here is the same as the surface I'm showing over here. So what is going on right here? What's happening here? Dipping? It's a dip? Or is it a peak? Is it a hill? It's a hill because the gradient vectors are pointing in direction of max rate of change. So if they're pointing towards the center, you're going, that's maximum rate of change, right? So which hill is that right there? Here's the XY, here's the origin right here. So it's this one right here, right? Okay. And then what is this showing here? That's your dip, right? That's your dip. What direction is greatest rate of change? The away from the center of the dip, right? Heading up. And then what happens to these vectors as you get away from either the max or the min? Increase, right? Because near the max and min is going to be the shallowest rate of, or the least rate of change, and then as you get away, the rate of change is going to increase. And what's true about the relationship between every gradient vector and the contour lines? Orthogonal, right? Orthogonal, right? So the whole field is going to be all vectors orthogonal to all the contour lines. Okay, are all vector fields gradient fields? Are all vector fields gradient fields? Are all vector fields gradient fields? No, just in general. There's only one vector field here, right? So are all vector fields gradient fields? No. So gradient fields are a very, very special class of vector fields that they happen to be given some what we call potential function. That surface or this original function was what we call the potential function. There's only one gradient field associated with a potential function, right? Showing direction and magnitude or rate of change everywhere. It's kind of like a gradient field is kind of like it's one representation of the derivative of the function, right? Because it's what? It's showing us the direction of rate of change at every point, right? And just so it's max rate of change. Yeah, Ezra.
We wouldn't be asked to like draw the gradient field on the left without the graph on the right, because we wouldn't know whether or not it's going up or down at that point without like if we were given the function as well.
Well, I mean, so it might take some time, but you could still, yeah, you need the function or the surface, one of those two. Yeah. Either any of the three. If you had the function as a formula like that, if you had the surface, or if you had the contour plot, all would give you the ability to sketch, at least crudely, what the gradient field was. Yeah. Okay. Other questions? All right. So how about this then? Here's a vector field. Is it a gradient field? Okay, so if it were, then what would be true? So we kind of say, maybe, right? Maybe. And if it were, then what would 2 be? The partial derivative with respect to x would be 2. And the partial derivative of y would be, so we're not sure. We're just going to chase it out, right? So we're saying, is there some function f whose partial with respect to x is 2 and whose partial with respect to y is y?
Yeah.
Okay, so then according to this, if this is the partial with respect to x, we can get kind of one view of f. What would that one view of f be? That f of xy is 2x, but then what does the plus c entail? Just a constant?
Y and a constant.
Yeah, so there could be what? There could be any function of y, call it g of y, and there could be some true constant, right? So this is one perspective on f taken from the partial with respect to x. So then we're going to write another, we got another perspective on f. So here's another way to write f, given that this is the partial with respect to y. So, what would this perspective of f, giving this information, what perspective of f do we have? So we'd have what? 1/2 y squared plus some function of x would be possible, right? Does there have to be a function of x? No, there could be, right? Plus some constant. So now, these are two views of the same function. These aren't two different functions, right? These are both views or perspectives on f. And if we can resolve them into one f that agrees with both of them, then that was a gradient field, and we've got the potential function. So can we do it? Can we resolve those two to be the same function f? So here, look, our 2x is the h of x. Our g of y is the 1/2 y squared, and then maybe there's some constant. So it looks good. And so we could write f as 2x plus 1/2 y squared plus c. And then this would be its gradient field. And how can you check it? Take both the partial derivatives of that, and you should get 2 for the partial derivative of x, and y for the partial derivative of y. And you do. So we got it. Okay, so what about y comma 1? So partial derivative with respect to x is y, and our first view of, or first perspective on f is xy plus potentially just a function of y plus c. And if the partial with respect to y is 1, then we get another kind of view or perspective on that same function, right? These are, we're trying to write the same function based on the two different pieces of information. It would be what? We potentially have a function of x plus y plus c. So, can we resolve these to be the same function? Can we write a function that fits exactly this form and also fits exactly that form?
No.
So what about,
Because if you take the partial derivative of y,
that's good. That matches up. So here I've got xy. That means I have to have xy down here, or something that could be like xy. Do I? Nope. So this is a problem. There's no xy in this one. So there's no way we could write f that satisfies both this form of it and this form of it. So their conclusion, not a gradient field. There's no function f that you can write whose partial with respect to x is y and whose partial with respect to y is 1. It's impossible. Make sense?
It's not that.
No, there's no function whose gradient field is that. So that's a valid vector field, but it's not the gradient field of any function. Yeah. Okay. Oh, do we have written homework?
No.